Hi, I'm Gurusha and I'm presenting my paper LM2, A Simple Society of Language Models Solve Complex Reasoning. This work was done in collaboration with Subhabrata Dutta and Tanmoy Chakraborty from IIT Delhi. Language models are becoming increasingly powerful, but when it comes to multi-step problem solving, they often lose track of the solution and make mistakes that do not agree with the past steps. There exist least to most prompting and DASLAM that guide the language model by generating sub-questions. Typically, the decomposition is done in a memoryless manner with or without the solver's initial response. No strategy is employed to track whether the solver can follow the decomposed chain of reasoning. To solve this, we propose LM2 that is built upon three separate language models: decomposer, solver, and verifier that are dedicated to different components of multi-step reasoning. Here we show the inference procedure of LM2 on a question from math dataset. The question in blue is provided to the solver language model that produces an incorrect answer in red. The question is then provided to the decomposer language model that generates the concepts and the step-by-step sub-questions in lilac. Each sub-question is answered by the solver language model and the sub-answer is verified by the verifier language model. If the verifier language model approves the sub-answer, then the answer and sub-question pair is added to the context of reasoning steps. Otherwise, a new sub-question is generated. The question, concept, sub-question, and sub-answers are provided in context to the decomposer language model to generate the next sub-question. Finally, the question, concept, sub-question, sub-answer are provided to the solver language model to generate the final answer in green. Language model is built upon the coordination of multiple language models to perform reasoning in a modular fashion. However, such coordination is not implicit in the pre-training stage of a model. Instead, we seek to inculcate this ability via fine-tuning parts of language model multiplex. The decomposer language model. The decomposer guides the solver language model to solve a multi-step reasoning question in two ways. First, it provides the solver with the set of concepts that it is required to solve the problem. Second, it tells the solver what is the next sub-questions required to solve the given question and the previous sub-questions and their answers. The decomposer training is performed in two stages. The first stage is supervised fine-tuning, where the language model is fine-tuned on a data set prepared using GPT-4. To create the data set, we provide GPT-4 with a question and its goal reasoning. Then it is asked to generate all the concepts required to solve the questions, followed by the sub-questions and sub-answers. Only the questions that were answered correctly were included in the dataset. As a second step of training, we utilize PPO with solver and verifier model as the black box environment. We will detail this in the next slides. The verifier. Given the complexity of the multi-step reasoning, we need the verifier to be able to provide nuanced feedback to the decomposer on the possible mistakes made by the solver. A binary correct or incorrect message as employed by the prior work with verifiers will limit the decomposer model's scope of vision. For fine-grained control, the verifier is fine-tuned on a supervised dataset containing question, answer, with an error made in the correct answer, a classification for the type of error, and explanation for the classification. The verifier classifies the given input into 9 classes as shown in the slides. The decomposer, second part of the training, policy optimization. The training dataset curated for the decomposer language model only contains the correct answers. Hence, the decomposer is blind to the possible errors made by the language model. In order to make the decomposer generate meaningful questions, we further fine-tune the decomposer while working in synergy with the language model using policy gradient methods. The reward is based on the feedback given by the verifier at each sub-question produced by the decomposer. The reward function is as shown in the slides. For all the experiments of LM2, we use OpenAI Text DaVinci 003 model as a solver and Llama 213 billion as the decomposer and the verifier. For the first stage of fine tuning, we curate a dataset using the train split from the MAT dataset. For testing, we perform tests on JEEBench dataset that not only contains math questions but also questions from physics and chemistry domains. Results. We can see that LM2 generally outperforms all the existing prompting techniques with GPT 3.5 as the solver. In 3 out of 12 cases, LM2 even outperforms GPT 4. In the figure, we depict the average number of tokens generated by the solver model while using different methods, and can see that the token consumption of LM2 is less compared to DASLAM and COT. To further understand the nuances of LM2, we perform an analysis of the generated output on examples from MAT dataset. As we can see that GPT-4 makes an incorrect interpretation of the question itself, whereas the subquestions produced by DASLAM do not adhere to the order of reasoning required to solve the problem and generate redundant questions. With LM2, we observe a much more well-defined crisp line of questioning by the decomposer model. The solver model is able to reach the correct answer option without regenerating the same information or drawing incorrect sub-answers. That was our paper, and thank you, and here's a link to the paper for further reading.